Okay? Then I wanted to go back to this proof, and I said that there's something about the proof that I don't like, which is the switching. And I want to give you a different perspective on the proof, which is a nice segue to the next topic that we have. So let's go back to this notion that about the tableau. And remember, I said each symbol in the tableau is a fixed function of a constant number of symbols in the previous configuration. Right? And this is because M is deterministic. So if you take any deterministic Turing machine, then each symbol is a fixed function of a few previous symbols. What this suggests is instead of trying to build a formula, because the problem with a formula is you need to choose what the tableau is, why not build a circuit? Suppose we built a circuit where the inputs were exactly x1 to xn. So you feed those as inputs. And those inputs will determine what happens in the next, which determines what happens in the next, so on and so forth. So what this means is, I will write this down as, I'll write it down as a formal theorem. I write it down as a formal theorem. Well, first let me draw some pictures and I'll write it down as a formal theorem, is that if M is deterministic, then each symbol of the tableau can be computed by a fixed function of a constant number of symbols from the previous configuration string. So if I were to write down the tableau in binary, so I have t, little t is time, and I is, so t, little t of I, is some fixed function, and so this is just some function that I can write of the array of characters from t minus 1 to I minus some theta of 1, going all the way up to t, well, I could just look at the interval of symbols, t minus 1, I plus theta of 1. Right, so I'm looking at this as sort of as an interval. And I say plus minus theta of 1 because, of the binary encoding, so you need to look at a few symbols to the left and a few symbols to the right. Now this can be computed by a circuit of O of one size. Okay, so what is a circuit? Let's just formalize what a circuit is. So a circuit is a DAG where leaves are labeled with the inputs, and intermediate nodes are labeled with AND or NOT gates. The fan-in, so the fan-in is the number of inputs to each gate. Okay, and we will assume that this is going to be, 1 or 2. So if it's a NOT gate, it has one input. If it's an AND or OR gate, it has two inputs. You can think of situations where the fan-in is unbounded, but let's not worry about that for now. The fan-out Note that if it's a DAG, so maybe, we use, but this symbol could be fed to many different places, right? There could be many wires that you could use. The fan out can be unbounded. So this is the setting we'll consider. You'll see that most of these don't really depend on these explicitly, but for now, let's stick with this. The fan in is bounded and the fan out is unbounded. So this is what I call a circuit. It's a DAG. So here the inputs are labeled with the symbols here, and you have a DAG to compute T of I. So what this means is, because each symbol can be computed by a constant sized circuit, all entries in the tableau, all entries in T can be computed by a polynomial sized circuit. And so can the output. So can the output, of course, being accept or reject, right? Accept or reject. So what this means is that given the Turing machine M and an input size n, this is going back to what I said earlier, which I was confusing, but given M and an input size n, there is an algorithm that constructs a O of T of n squared sized circuit in poly Tn time and O of log Tn space. Right, so you're just given the Turing machine and a size, and you're spending time that is polynomial in the running time of the machine that constructs a circuit, and I will refer to this circuit as C of Mn, such that M accepts the input X if and only if Cmn evaluated on X is 1. Okay, and this is worth stating as a theorem. This is like looking at the Cook-Levin construction. Given a Turing machine and an input size, in T of n squared time, you can poly T of n time, you can construct a circuit of size T of n squared such that the circuit accepts X if and only if the Turing machine accepts X. So you can convert Turing machines to circuits. Does this make sense? Any questions? So actually, in some sense, if you think about it, okay, so first any questions about what this means? Okay. So now, with the circuit view in place, now we've talked about algorithms, but now it seems like we're talking about circuits that compute functions, which in some sense is almost actually a more easier way to think about something computing a function. It's a circuit rather than a Turing machine, which has loops and other crazy things that lead to undecidability. What about thinking about circuits? So let me just give a few obvious definitions here. I'll say a circuit C of n on n inputs computes a function, a Boolean function. So if for all x of length n, sort of the obvious thing, Cn of x is equal to f of x. And then, now the problem is with a circuit, the number of inputs is fixed. So we'll say a language L is decided by a circuit family. So actually what I'll do is I'll use normal letters for a circuit, and a family I'll use the scripted, where this is a family of C1, C2, so on and so forth. It's just an infinite set of circuits, such that for all x of length n, x is an L if and only if sort of the obvious if Cn of x is 1. Right? So this is called a circuit family. Does this make sense? What a circuit family is? And we'll say a circuit family C has size S of n if for all n the size of the circuit is O of Sn, sorry, size, and the size is equal to the number of gates or nodes. You could also optionally count the number of wires, but I'm just going to count the number of gates. This is now essentially a different complexity measure. It's almost like a different viewpoint on functions. Instead of algorithms, we can think about circuits. And one of the things that circuit complexity as a field tries to do is to try to understand how circuit complexity, which is the size of a circuit that computes a function, relates to notions like time and space complexity, which are what we think of as algorithms. Any questions about this definition? So a circuit family has size Sn if for all inputs lengths n, you look at the circuit of that size. So think about a circuit family as almost like providing a different algorithm for every possible length. Like when you think of an algorithm, you think of one algorithm has to work regardless of the input size. Like that's what an algorithm is about. For a circuit, it only has to work for all inputs of a given length. This makes sense? Now, when we've talked about polynomial time and polynomial space, we can also think about polynomial size. And this gives one of the crucial notions here, which is we'll define size of Sn to be is the class of languages is the class of languages decided by circuit families of size Sn, so obviously. And now our notion of P, it's called P/poly. And I'll explain later on, in the next few lectures, we'll see why this notation is used. So P/poly is sort of your natural guess as to what it is. It's all functions that are computed by polynomial-sized circuits. Let's go back to this theorem that we talked about, which is the Cook-Levin construction. It says given m and an input size n, there's an algorithm that constructs a t of n size squared circuit in this much time such that this happens. So what does this imply? What does this theorem imply in terms of P/poly? Can you relate P/poly to any known classes that we have now?
Seems like P is in P/poly.
P is in P/poly, right? I mean, it's even better, right? That for P/poly, we merely want the existence. Here, we even have an algorithm that computes the circuits for us. But you're absolutely right that P is in P/poly. And actually, I can do even better. I can show it's a strict subset. There exist functions that are computable by polynomial-sized circuits that cannot be computed in polynomial time. So for the proof, I'll say we showed above that P is a subset of P/poly. Okay, why is it a strict subset? Why is P/poly a strict subset? I claim that you already know the answer in the sense that you can come up with a language which is in P/poly but not in P. Let me phrase this question differently. For any function whatsoever, can you come up with a circuit family that computes it? All right, so let's see if I can.
Seems like you might not be able to do like busy beaver function.
Using.
Maybe you can. I mean, if you knew what the numbers were, I guess you could. But
so here's what where the struggle. You're saying that there is probably no algorithm that can compute that circuit.
yeah, but I guess there is a circuit. There's just no.
But it exists. Right, simply because for any function, you can always write a circuit that just hard codes the inputs and outputs. Like you build a multiplexer. What is a language? Or what is a function? A function is a truth table. Every truth table can be converted to a circuit. That meaning there exists a circuit that computes the function that computes a function. Okay? Okay, now let me make a claim over here. And this is almost a seemingly trivial claim. Every unary language is in P/poly. Every unary language actually can be computed in P/poly. Why?
It's a simple and.
Sorry, with a simple? Yeah, no, the answer is
a simple
trivial.
and.
Yeah. So yeah, what
You just and the bits.
okay. Okay, you just add the bits, good.
Understand
But if it's
language.
unary, there could be some strings of length n that are not in the language and some that are. Unary doesn't mean that all, not every string with all ones is in the language. Some of them are and some are not.
But you can just have like a for every string that's no.
No, you're almost
Yeah. Because you just like for every string that's not in the language, you just there's like some one where it shouldn't be one or whatever.
I mean, you're allowed to
Exactly.
define a separate circuit for every size.
Yeah.
Right? So if 1 to the k is not in the language, then ck just outputs 0.
Oh. Sure.
And if 1 to the, okay, so every unary language is in p/poly, so I'll just write on y. So if 1 to the k is in the language, then ck does an AND of all inputs. If 1 to the k is not in the language, ck outputs 0. That's it. So it's a linear sized family, right? Because to take the AND of all the inputs, you need linear size. But otherwise, you just output 0. So every unary language is in p/poly. Okay. Now that every unary language is in p/poly, how do you find a unary language that's not in p?
Now just do something undecidable like
Exactly, right? You just take the halting problem and encode it in unary. Right? So you could simply take the language unary halt, which is 1 to the k, where k is equal to, let's say, the representation of mx in the halting problem. Right? So you basically take every instance in the halting problem or the halting language, and you just encode that as an integer, and you say 1 to the k. So unary halt. So this is undecidable. But it's in p/poly. And so that completes the proof. So hence, P is a strict subset of p/poly. Okay? So that was, and again, to prove that it's, the inclusion is non-trivial because that requires a Cook-Levin type construction. So one of the questions we could ask is that could NP be in p/poly? And indeed, we'll talk about this in the Karp-Lipton theorem, about what kinds of implications that has. But that was actually one of the approaches then proposed towards proving that P is not equal to NP, is that seems really hard. But maybe if we think about circuits, it is more convenient. So circuits are in some sense a more convenient model for lower bounds, or at least it is believed. The circuits are more convenient from a lower bound perspective. And so this is actually proven way back by Shannon. So what Shannon proved, and I'm just getting the year, in 49, this was also proven by Lyapunov, is for every n, there exists a function fn that requires a circuit of size omega 2 to the n divided by n to compute. So you could ask, could all functions be in P/poly? And the answer is no. There actually exist functions that require exponentially large circuits, although it's annoying that there's actually a 2 to the n divided by n. It's like, why is there a divided by n here? So what is remarkable is for all functions f, which are, n input functions, all functions f can be computed by a circuit of size O of 2 to the n divided by n. So 2 to the n divided by n is actually the right answer. You can get to 2 to the n without much difficulty. You can show that there exists a circuit of size 2 to the n basically by doing some kind of multiplexer. You can do some kind of induction. But to actually get it down to 2 to the n divided by n, that requires some cleverness. There's actually a very subtle choice of parameters where you get that to work. So my agenda for, we have about 15 minutes left, so I can talk a little bit about one of these bounds. I will prove Shannon's theorem in all of its glory. And then we'll talk more about circuit complexity, which I think is again one of the interesting techniques that has been, at least we can prove some lower bounds, although they're very weak, but we can prove some lower bounds in circuit complexity. Okay, so let's begin. So any questions about this? Any questions? I know it's a bit late, but I still would like to take like a break for about 2 minutes, just to give everyone a pause. So about 2 minutes, we'll take a break, and then when you come back in the next 10-15 minutes, I'll talk about how one proves the first part of Shannon's theorem.
Sish?
Yeah?
Question. You said about the size bound that you just talked about, 2 to the n over n.
Yeah.
Is it done through reusing the gates that you?
Yeah, you have to reuse the gates. So this is not a formula. So a formula is a tree. So in this, you actually have to reuse computations. Indeed, that's exactly what they do. What they do is, the argument for this proof is you actually pre-compute all functions of a few inputs, and then you can reuse those. And if you kind of choose it, you have to choose it very carefully, but if you choose that carefully, you get 2 to the n divided by n.
Oh, cool. And does that like give you a binary tree style logarithmic decrease in size? In each step, am I imagining it correctly? Like you pre-compute everything, and then from those pre-computations, you can do another step, and so on and so forth?
No, it's not an induction. It's actually not. No,
okay.
That's what's. It's kind of subtle. What you do is, no, it's not that. It's actually just a two-step process. You'll see when you'll see the proof. It's
Okay.
it's some kind of calculus magic.
Thank you.
Okay, so let's do the first part, because the first part is actually a relatively simple calculation. The second part is more magical. So part one, but even then it was, it takes some insight to realize that there's a 2 to the n missing. So the idea is basically, this is sort of a classic technique in discrete math. It's what's called a counting argument. And the counting argument simply says there are more functions on n inputs than there are circuits with 2 to the n divided by 2 gates. So if there are more functions than circuits, then obviously there has to be a function that cannot be computed by the circuit. Okay, so let's start with the first part. How many n input functions, Boolean functions? So how many functions on n bits are there? Classic bound. How many?
Well, for every string, it's either in or not in the language.
Yep.
So,
2 to the 2 to the n.
2 to the 2 to the n, exactly. It's 2 to the 2 to the n. Why? There are 2 to the n inputs. Each input is either in the language or not. Is either yes or no, or true or false. Right? It's just saying that here's the truth table. Right? And the truth table gives an output over here, right? So this is the input. And the size of this input is 2 to the n. And each of these is either a 0 or a 1. So you get 2 to the 2 to the n. Great. So what we are now going to do, and this computation is a little bit more careful, is you have to count how many circuits there are with 2 to the n divided by n gates. So let's actually abstract that out and instead say how many circuits with n inputs and 2 to the n. No, instead of 2 to the n, let me just call it s and s gates. Okay, so let's kind of think about, abstractly speaking, how do you represent your circuit? Well, for every leaf, you have to specify which input is associated with the leaf. So the representation so one is you specify the label, which is the input label, input variable, of each, I call it a leaf, but it's basically a source. It's a source in the DAG. Then you specify the type of each gate, which is stored at a node. And finally, what you need to do is specify the out neighbors of each gate or node. It's like giving the adjacency list. It's like giving the adjacency list. Okay? So instead of specifying the out neighbors, which could be many, I could instead just specify the in neighbors, which would be equivalent. Instead of specifying out neighbors, specify the in neighbors. That's like saying that to give the adjacency list, I can either specify the out list or I can specify the in list, but they're both equivalent in terms of what they represent, the object. So if I can give the label of each leaf, I can specify the type of each node, and I can specify the out neighbors of each gate, or specify the in neighbors of each gate, then I have given a full representation of my circuit. Right? Okay, so let's kind of break each of these up one by one. So a source is labeled x1 up to xn. It could also be labeled 0 or 1. Let's just assume that we have these extra in our circuit. We may want to sort of hard code something as a 0 or a 1. So we have the sources are labeled x1 to xn, and we'll say that how many sources do we have? We'll assume that there are n plus 2 sources, right? Because you want to have a separate source for the 0 and 1. So the number of these is just n plus 2 factorial, or n plus 2, let's just say it's n plus 2 to the power n plus 2.
Wait.
Each of these, we have n plus 2 choices. Yeah?
Why do you need to do this? Why not just say like, well, like it doesn't matter which node you call x1, as long as you remember like which node gets the input from x1, right? So if you're specifying the in neighbors, can't you just say like every single function on n variables is going to have these n nodes and they're all going to be the same every time?
You could. What you're saying is like hard code that representation for all possible functions.
Yeah.
Like the nodes labeled 0 up to n plus 2 have exactly these values.
Mm-hmm. Yeah.
Yeah, you could do that. This is actually going to be a lower order term. You're right.
Okay.
One can remove this. So part 2, the number of types of each gate, right? So the part 2 was to say, what is the type? Sorry, this is for the focus. The type of each gate. So there are 3 types of each gate. And so we'll just say it's 3 to the s. Now the interesting one is to specify the out neighbors of each gate. So each gate, okay, so how many out neighbors? So how many in neighbors can it have? It has 2 in neighbors at most. How many choices for the in neighbors? How many choices for the in neighbors? Does that make sense? So each gate has at most 2 in neighbors. For each in neighbor, how many choices are there?
Like n or s rather?
S. There are s choices. So the number of again, I'm just giving upper bounds here. The number of choices is at most s squared choices of in neighbors of pairs of in neighbors, right? Of both in neighbors for each node. And so the total is s to the power 2s. And the fact that you get s to the power 2s is actually going to give you that log n. It's going to give you that n factor that's there. Okay, so the total number of different circuits, with s nodes is at most n plus 2 to the power n plus 2 times 3 to the s times s to the 2s. And indeed, as was mentioned, the first one could even be removed. You could even remove this if you're more careful. So this is basically like hard coding the input sources. But the point is you have 3 to the s times s to the 2s, which I'm going to write as this is 2. There's some constant there of log s. 2 to the, what am I saying? 2 to the s plus s log s. So you get an s log s because it's s to the power s is like 2 to the s log s. Okay, does this make sense? So the number of different circuits, I can basically say this is 2 to the theta of s log s. Okay? And so there's some constant over here. In this case, the constant it's probably a fairly small constant. I'm just, I'm doing it a little sloppily. I'm pretty sure that I can probably prove that this is at most like 5. Like this is at most 2 to the, I'd say 5s log base 2 of s. Okay, so suppose s is equal to 2 to the n divided by Cn, where this is some constant. Then what you get is 2 to the 5s log base 2 of s is equal to so I'll just write this as 2 to the power 5 times 2 to the n divided by Cn times log of s. So log base 2 of s is going to be n, minus whatever, log base 2 of Cn. But observe that this n cancels out with this n. Right? When I'm doing an upper bound, I can essentially cancel these two from each other. As long as the c is sufficiently large, this is going to be strictly smaller than 2 to the 2 to the n. So this is in some sense the piece of math that you need to see. The 2 to the s log s, when s is 2 to the n divided by Cn, then the whole thing computes to be less than the total number of functions. So hence, there is a function on n inputs that is not computed by a circuit of size, you can even say at most, 2 to the n divided by Cn. Right? So to compute this function, you need at least 2 to the n divided by Cn. And that gives us our lower bound. This is a counting argument. And so I wanted to show you this to show you that unlike discussing algorithms where it's really hard to prove lower bounds, with circuits sometimes it's often easier because you can actually count explicitly the number of circuits of a given size. But you cannot count the number of polynomial time algorithms. But you can count the number of circuits of a given size, and you can kind of exploit that information to get a lower bound. So that proves that there exists a function that requires a circuit of size omega 2 to the n divided by n. And there's a counting argument that I laid out over here. The next lecture, we will do the second part of Shannon's theorem. We'll actually show that f can be computed by a circuit of size 2 to the n divided by n. And then from then on, we'll continue to more discussions of circuit complexity and how it relates to time complexity. All right, so we'll end here, and I will see you all in person on Tuesday.